Hello, dear friends. Today we will discuss another type of filtering approach, that is adaptive filters for removal of interference. Filters with fixed characteristics, we can say tap weights or coefficients, are suitable when the characteristics of the signal and the noise are stationary and they are known. But these filters are not applicable when the characteristics of the signal and or noise vary with time. For example, consider the situation when two ECG signals, such as those of a mother and fetus, gets recorded and added in the same proportion. The spectra of, you can say, the spectra of such type of signals have generally the similar frequency ranges, and hence fixed filtering cannot separate them. So such a situation needs the filter that can adapt to the characteristics of the interference, estimate the interfering signal, and finally remove it from the mixture to obtain the desired signal. So now the problem is to design an optimal filter to remove a non-stationary interference. If you remember, we have already discussed about optimal filtering. But here we want to design an optimal filter which is used to remove a non-stationary interference from a non-stationary signal. Previously, we have studied for the stationary signals, but now adaptive filtering is mainly suitable for a non-stationary kind of interference from a non-stationary signal. The filter should adapt continuously to the changing characteristics of the signal. Assuming an additional channel of information related to the interference is available for use. Now, how we can solve this problem? So, for this, two concerns need to be addressed. First one is the filter should be adaptive. That means now the problem is that we have to design an adaptive filter for which the tap weight of the filter will vary with time. So we can say it is adaptive, and the filter should be optimal. So we have two concerns which are to be addressed. One thing is the filter should be adaptive, and the other is the filter should be optimal. Now you can see this diagram. This block diagram represents a generic adaptive noise canceller, or we can say an adaptive filter. Here the primary input to the filter is Xn. As you can see, it is Xn, which is the mixture of the signal of interest, that is mainly Vn, and the primary noise, here it is Mn. That is, now we can say Xn is Vn, which is signal of interest, plus Mn, that is interference or noise. Now further, it is desired that the interference or noise be estimated and removed from Xn to obtain the signal of interest, that is Vn, and for that we are assuming that Vn and Mn means the signal of interest and the noise are uncorrelated. This is the assumption we have to do. Now, adaptive filtering requires a second input, which is known as the reference input. Now, you can see in this figure again, we have this reference input. So, one is primary input, and in this adaptive filtering, we need one reference input, you can see this is Rn. So this Rn, which is again uncorrelated with the signal of interest, that is Vn, but it is closely related, or we can say it is correlated with the interference, or we can say noise, which is Mn. So the adaptive noise canceller, or we can say adaptive filters, modifies this reference input to obtain a signal Yn, which is as close to the noise Mn as possible, and then Yn is subtracted from the primary input to estimate the desired signal. So these are the equations which you can follow. So V cap n, you can see, or V oblique n is nothing but we can say an error signal, which is the desired signal Xn minus Yn, and Xn here is the combination of Vn plus Mn, and we are subtracting this Yn, which is the estimate of some kind of noise. We can say Yn is nothing but we can also keep it as M oblique n, and it is the estimate of the primary noise obtained at the output of adaptive filter. Again, you can refer to the figure also. If you see, we have primary input, we have reference input, and this reference input we are keeping to this adaptive filter, which has varying tap weights, and the output of this is Yn, which should be closely related to noise, and then when we are subtracting this Yn from Xn, we are getting En, and our motive is to minimize this En, and for that we can, this En is nothing but it is input to this adaptive filter, and by varying the tap weights we can assume this Yn should closely represent that kind of error, and we can subtract to obtain desired signal, that will be Vn. Okay. Now as I mentioned, we have now error equation, that is En, and we want to minimize that error. So what we will do is, we will take the square of this, and expectation means mean of both the sides, because we need mean square error, because every time our motive is to minimize that mean square error. So we are taking square of that error function, and finally expectation operator we have applied. So we can apply, and if you keep the equation of En from this equation number 2 to this equation, you will get expectation of V square n plus expectation of like Mn minus Vn whole square plus 2 expectation of this Vn into whole Mn minus Yn. Basically we are keeping the formula of A square plus B square minus, or we can say plus 2ab if it is plus, and what we have done is we have taken this Vn is one signal, let's suppose A, and this Mn minus Yn as B. So we are keeping the formula of A plus B whole square we are doing. So A square plus this B square and plus 2AB. So we are keeping this, which side? We are keeping this expectation operator. So this is equation number 3. Now, as we know, Vn is uncorrelated with Mn and Yn, but all of them have zero mean. So we can keep this equation number 4, you can see expectation of Vn into this Mn minus Yn, or we can keep it as, we can separate these two because they are uncorrelated. So expectation of Vn into expectation of Mn minus Vn, that should be equal to 0. So if you keep this equation number 4 in 3, then finally we can write that equation as expectation of that mean square error, or I can say square error. It will be expectation V square n plus expectation of Mn minus Yn whole square. Now further, it can be noted in figure 1, as we have seen, that the output En is used, which is basically fed back to control the adaptive filter. That already we have seen in the figure. Now, in adaptive noise canceller applications, the main objective is to determine En that corresponds to least square fit to the desired signal Vn. And if this is achieved, how this can be achieved? This can be achieved by feeding the output, that is nothing but error function, back to the adaptive filter, and then what we will do is we will adjust the filter, means we will vary the tap widths or the filter coefficients to minimize the total system output power. Now, what is signal power? How it will be affected? The signal power is nothing but E V square N, because V is basically your actual signal. So square of that and taking mean is nothing but power will be unaffected as the filter is adjusted to minimize this mean square error function, and therefore the minimum output power, that is minimum of expectation E square R. Now it is mean square error, you can say, or we can say minimum mean square error MMSE, that it will be again expectation V square N plus minimum of this function expectation of Mn minus Yn whole square. Now as the filter is adjusted so that the expectation of this E square N is minimized, then this function, that is expectation of Mn minus Yn whole square, is also minimized. Thus, the filter output Yn is the minimum mean square error, as I mentioned, MMSE, estimate of the primary noise, that is Mn. Moreover, even if this expectation Mn minus Yn whole square is minimized, you can say En minus Vn, it will be also minimized, as from equation 2 we can say En minus Vn is nothing but it is equal to Mn minus Vn. If you want, we'll just go through equation number 2 again. You can see it is from this En is nothing but Xn minus Yn. So Xn is what? Vn plus Mn. So I can write En minus Vn. If I take Vn that side, so you can say En minus Vn is nothing but Mn minus Yn. So if this Mn minus Yn square expectation is minimizing, so that means it is equal to En minus Vn whole square expectation will also be minimized. So this is the equation. You can say equation number 7 if you use, you will get expectation of En minus Vn, which we are keeping instead of Mn minus Yn whole square, that will also be minimized. So by adjusting the filter to minimize the total output power, that is to cause output En to be Vn, or I can say to be the minimum mean square estimate of the signal of interest Vn for the given structure, and adjustability of the adaptive filter and for the given reference input. Therefore, from equation number 7, from the equation number 7, you can see the output noise is given by again En minus Vn. So we can keep this En as the estimated V, or I can say estimated signal V oblique N, that is again equal to Mn minus Yn. Now it can be analyzed that by minimizing this mean square error, it minimizes the Mn minus Yn whole square expectation, which further minimize the total output power, and it minimizes the noise power. So we can say output noise power. Now the signal component Vn in the output remains unaffected. Now minimizing the total output power, it will maximize. Basically when we minimize the output power, it will minimize the noise, but the signal component will remain unaffected. So what will happen? It will maximize the SNR, that is signal to noise ratio. So from equation 5, you can see the equation 5 once again. So this is equation number 5. You can see this equation. You remember this equation. So what we can achieve from this equation number 5? It can be said that the output power is minimum when this E, or I can say expectation of this square error, is equal to expectation of the desired signal square, and at this point this error function will be 0, and then we can say yn is equal to mn, and if yn is equal to mn means the estimated output of, we can say, the adaptive filter, if it is equal to that noise which actually we are subtracting from xn, so in that case en will be vn, that is what actually output we want, and we can consider that output is a perfect and noise free estimate of the desired signal. So we can estimate that it is a noise free estimate of the desired signal. Now, optimization of the filter. It may be performed. Now we have designed a adaptive filter. Fine. First thing was that we have to design an adaptive filter, and we have seen the conditions. Now, how we can achieve optimization? Because second concern was that the filter should be optimal filter. So how we can obtain that optimization part? So optimization of the filter, it may be performed by expressing the error in terms of the tap weight vector and then applying the particular method. It can be least square method or any other which we want, or Greiner filter we can realize with this, whatever is available. So the output Yn of the adaptive filter in response to its input Rn, because if you have seen in the diagram that for adaptive filter output is Yn and input is Rn. You can again refer to that diagram. Just we'll refer once. So this was the adaptive filter. So input is the reference input, we are considering Rn, and output is the Yn. So for optimal condition, what we are saying is, so how we can represent that if it is an adaptive filter, how we can represent this output Yn of that, considering Rn as the input. It is again we can use this convolution type equation, because actually we are finding the output equation and we know this input, and what is the impulse response, those we can give in terms of tap weight. So here W key represents the tap weight and M is the order of the filter, where K is running from 0 to M minus 1. So the estimated error, which is En, or we can say the output of the adaptive noise canceller, it will be En is equal to Xn minus Yn, as already we have seen. So we have to define the tap weight at time n, we can define as Wn, which is, because we are considering M order filter, so it will be W0 n, W1 n up to Wm minus 1 n transpose. We are taking a matrix in terms of matrix. Similarly, the tap weight input vector, what will be input vector? Means Rn is the input, so if we are considering as vector, so it will be again M dimensional we have to consider. So it will be Rn, means we will take delays. How many delays we have to take? M number of delays we have to take. So it is Rn minus 1 up to R of n minus M plus 1. Actually M minus 1 delays we need, because one is the present signal, that is Rn, and remaining M minus 1 delays we need if it is a M order filter. So thus the estimation error En may be rewritten as, En is nothing but in terms of matrix, if I want to write Xn minus, now here it was Yn, but instead of Yn we are keeping that in terms of Rn, which is the input, and Wtn, which is nothing but your impulse response matrix or tap matrix or tap vector. So Xn minus W transpose n Rn. So that corresponds to the error equation. Now, several methods, as I mentioned, they are available to maximize the output SNR. Means I want to increase the signal to noise ratio. The methods can be least mean square, that is LMS method. It can be recursive least squares, or RLS method, means we can say it as. So here we will take the least mean square adaptive filter, means what optimal conditions or what optimality method we are using, that is least mean square method. So we are calling it as least mean square adaptive filter. Now, as we know, the purpose of adaptive filtering is to adjust the tap weight vector Why we are adjusting that? Because we want to minimize the mean square error. That means we want to achieve minimum mean square error. So from equation 12, as we have seen just in previous page, so error equation is xn minus yn, but yn is wtn into rn, which is nothing but the output of adaptive filter. So if we want to minimize, we want to achieve the minimum square error. So what first we have to do is we have to square this. So squaring both sides, you will get e square n is equal to x square n minus 2xn Rtn Wn means minus 2ab plus b square. So here a minus b whole square we are using. So a square plus b square minus 2ab. So this squared error is a second order, or we can say quadratic function of the tap weight vector and the inputs, and may be depicted as a concave hyperparaboidal, or we can say bowl-like surface that is negative. Now, what is the aim? The aim of the filter is to optimize, and what is the what is the optimization procedure? Is to reach the bottom of the ball-like function. Means we have to reach the minimum function. We have to reach to minimum value, and where we will get that minimum value, because it is a ball kind of function. So that will be the bottom of that ball-like function. So the LMS algorithm is based on the method of steepest descent, where the new tap weight, we can say Wn plus 1, is given by the present tap weight, means Wn vector, which is Wn plus a correction proportional to the negative of the gradient, that is delta n of the squared error. So in terms of equation, if you see, that is Wn plus 1 is nothing but means next, because we have to make the tap weights adaptive to achieve that optimality condition, or we can say minimum mean square error. So what will be the next weight? If we want to change that weight, so that will be Wn plus 1. What it will be? It will be Wn minus mu into delta n, and delta n here is the gradient. Now the parameter mu, it controls the stability and the rate of convergence of the algorithm. The larger the value of mu, the larger is the gradient of the noise that is introduced, and the faster is the convergence of the algorithm, and the vice versa. So the LMS algorithm approximates delta n. How it will be approximate? By the derivative of the squared error in equation 13. If you see, if you want, I will just show you equation number 13. This is what we have achieved by considering the square. So with respect to tap weight, now what we are doing is we have to basically we have to take the derivative, because we have to minimize. So minimize means we have to take the derivative and keep it equal to 0. And if we are using that equation, it will be, we can say, del delta n is equal to minus 2xn into Rn. If you differentiate that equation, you will get this equation plus 2 again Wtn into Rn, again into Rn, because we are basically differentiating with respect to tap weight vector. So it will be equal to minus 2 En into Rn. Using this estimate of the gradient in equation 14, we get Wn plus 1 is equal to Wn plus 2 mu En into Rn, because there it was. You can see that equation again, this mu into delta n. So we have to keep the value of this delta n, and if you keep the value of delta n, basically delta n, it will be minus 2 En into Rn. So I kept in this equation, and this is basically known as Wiedrohoff LMS algorithm. So it is known as Wiedrohoff LMS, least mean square algorithm. Now, what are the advantages of this method? The advantage of the LMS algorithm lie in its simplicity and ease of implementation. Also, the expected value of the tap weight vector converges to the optimal Wiener solution when the input vectors are uncorrelated over time. And another advantage is The procedure may be started with an arbitrary tap weight vector and it will converge in the mean and remain stable as long as mu is greater than 0. But the less than the reciprocal of the largest eigenvalue of the autocorrelation matrix of the reference input. So this is one condition. So by this we can achieve a optimal, we can say optimal adaptive filter. So what was our concern is we have to design an adaptive filter. We have designed, and then other was we need to optimize that filter, and for that we have used the LMS algorithm, and we have find the equation for tap weight is how we will change the tap weight, what will be the next tap weight in response to the previous, or we can say the error function. So by equation number 14 we have achieved. So this is coming equal to, we can say, Wn plus 1, which is nothing but the new tap weight is equal to the old tap weight, that is Wn, plus 2 times mu into En into Rn. Rn is the reference input, En is the difference of, like we can say, Vn minus what is the output of tap weight or adaptive filter, and mu is our, you have to choose a kind of constant. So this is the equation of new tap weight. So we have designed an adaptive filter, or I can say optimal adaptive filter. So this was all in this lecture. Thank you.